Should this work?
You should have to turn that one on too.
Yeah, it's on green. Is it muted?
That's good.
Let's see.
That one's working.
1, 2. Oh yeah. That woke you up.
Okay. Hello, everyone, and welcome to the August Observatory Open House. So we run these open houses every month. Today we are live streaming it as well, so you can check these out from home on YouTube in our Queen's Observatory YouTube page. Before we get started with the talk, I just have one quick announcement. The Astronomy on Tap, which we announced at the last Observatory Open House, is not going to be running. There will be another one scheduled, and we'll tell you about it when that happens. All right, so that's our announcements. Our speaker tonight is Aaron Vincent, the professor here at Queen's University, but he hasn't always been here. He's actually traveled around quite a bit before we snagged him. He did his PhD at McGill University, then went on to the IFIC in Valencia, the IPPP in Durham, and he's traveled the world with, went to London for a while, and finally settled here as a faculty member just as of January 2018. So still new and still teaching us all sorts of cool stuff. The work that he does is pretty wide-ranging theoretical physics, but unlike most theoretical physicists, Aaron Vincent can actually make a connection to data. So,
I try.
The real world. So theorists spend their time coming up with crazy ideas, which is what we love them for. And Aaron tests these crazy ideas against data in our real world. So measurements that we've made, perhaps using measurements in ways that they weren't intended for in the future, and seeing basically a lot about dark matter, neutrinos, and cosmology, especially for dark matter. We know some things very well about it, and a lot of things not at all. So constraining what's possible, that's really his job. Now today, he's going to be telling you about the incredible expanding universe, and I'm going to leave that to Aaron. Please join me in welcoming him.
Thanks, Connor, for the very nice introduction. It's really nice to be here. I realize that I'm the one thing between you and seeing the universe right now, so I'll try to, or at least try to be interesting. Yeah, one advantage of being between theoretical physics and experimental physics is I get to make fun of both theorists and experimentalists, depending on which hat I happen to be wearing. Today I'm going to be pretending to be an astronomer. No, I am, sort of. And I'm going to tell you about some stuff that is tangentially related to the work I do. It's not directly related to the work I do, but it is extremely important in sort of the background understanding to getting to trying to understand the universe through the use of particle physics and cosmology and all these different tools that we have. So this is really some of the background. And in particular, I'm going to be taking a bit of a historical look at what we mean by expanding universe and how we got to that place. Are any of my Astronomy 102 students here? You weren't in my class. Now this is good because then no one's going to call me out on the fact that I've just taken a bunch of slides from my class. I didn't say that. You didn't hear that. Okay, so let's get started. And I want to get started with the Copernican principle. So this is this revolutionary idea from the, 16th century or something? I don't know, I wasn't there. That actually the entire universe doesn't revolve around us. We're actually on this planet that is orbiting the sun. And if you start to take that point of view, suddenly all these different astronomical observations that people had been making for millennia start to make sense, right? If you believe that the sun is at the center of this, what we now call the solar system, and the Earth is orbiting around it, and all these other planets are orbiting around it, you start to understand this weird behavior when you observe planets in the sky going back and forth. That's just really their relative motion, because we're in motion with respect to the sun and with respect to those planets, and they're also in motion. And suddenly you have this nice, circular, actually it's not quite circular, but close enough, picture of how the solar system works, and it just fits the data well. But it also tells us that we are not at the center of the universe. By the way, Copernicus wasn't the first person to think of this. Ancient Greeks had already sort of puzzled this out at a few points in history, but it kind of got buried beneath this geocentrist idea that persisted for a long, long time. But the extension of this Copernican principle is what's called the cosmological principle. And this is the statement, and this is borne out by data. If you look at the largest distances, if you look in any particular direction in the universe, everything looks pretty much the same. And there's no particular reason to believe that we're in some special spot. We, the sun, we, the Milky Way galaxy, right? So there's no special place and there's no special time in the universe. We just happen to be, in one particular spot, and we're observing the universe as it is, as we see it from our perspective. Some people call this the principle of maximum mediocrity. We're no more special than anyone else. Yeah, sure. So this brings us to a question which was put forward by Olbers, seen here looking a little bit disappointed at you. The cosmological principle, if we believe it, suggests that there's no edge to the universe. If there were an edge and we were closer to one edge than another, we would see more stuff on one side than the other. We don't really. Or everything looks the same all around us and we're at the center of the universe again. But if everything looks the same all around us, this sort of implies that maybe we're in this infinite, eternal universe. And in that case, why is the night sky dark? And the analogy is this. Say I'm in a forest that's very big, an infinite forest, or large enough for practical purposes. Every single line of sight that I will look at will eventually hit a tree. My entire sight line, no matter where I look in this forest, is going to end in a tree somewhere. So if I carry out that analogy to stars, well, there's a close star because we happen to be next to a star. But as I look further and further out, my line of sight should eventually hit a star. And the sky should actually look completely full of stars. If the universe is infinite and has stars everywhere, the sky should be this glow, this bright, bright glow. So why is this not what we see? Now, if you know the answer, don't yell it out. Spoilers. One possible answer is that there's stuff between us and those other stars. That actually doesn't work either, because in an infinite, eternal universe, that stuff would be heated up by all this starlight and then just start to glow, re-emitting that light, and the night sky would be bright again. So we'll go on a little journey to figure out why this is, and then maybe take it a little bit further after that. This whole story, so continuing on, there we go, got it, to the 1840s, sort of 1840s to 1925, people were developing, there's a scientific revolution, developing these more and more sophisticated telescopes, trying to understand how things were, what the universe was made of, and at that point the universe was really what we could see, local stars, the Milky Way, and these spiral nebula, which is what they were called, which are these cloud-like things that, well, they look like little spiral clouds. And so in the very beginning, around the 1840s, so this is William Parsons who drew these amazing pictures because there was no photography. So you had to wait until you saw these objects and then try to draw these detailed pictures and figure out what they were. The telescopes were still not powerful enough to actually resolve these, so this turns out to be the Whirlpool galaxy, as seen here by the Hubble Space Telescope. And there was no way at the time to distinguish all these. See, here we see these star-forming regions, so we know now that these are stars, but from this picture you can't really tell that they're individual stars. You just see this, this fuzzy mess. These beautiful hydrogen, if you see pink in an astronomy picture, you can just go, hydrogen, and you'll look really smart. But the only way to figure out what these were, so there are two hypotheses, either they're clouds within the Milky Way, or they're other island universes, other galaxies like the Milky Way. Immanuel Kant was actually a proponent of this idea. You need to figure out how far they are. If they're close, that means they're inside the Milky Way. If they're far away, that means they're extremely large and outside the Milky Way, right? So there are two ways of doing this. The first is to use angles, what's called trigonometric parallax. And this is the same reason depth perception works. You have two eyes, they're separated by a certain distance. If you hold your thumb out and cover, say, me, close one eye, close the other, your thumb moves, right? It moves from left to right. And the angle by which your thumb moves when you do that gives you a way to determine how far away your thumb is with respect to that very far thing that you're calibrating against. So instead of using the distance between our eyes, well, in astronomy, we use the distance between the Earth and the Sun. As the Earth goes around the Sun, we take one measurement of this angle between the star and very distant stars, and 6 months later, we take another measurement and use that angle and a little bit of geometry to figure out how far away things are. Now, we need a very large baseline because these are incredibly large distances, so incredibly small angles. And this only works in the local solar neighborhood. Up until last year, we couldn't go very far at all. Now with the new satellite called Gaia, we can actually start to map stars that are all the way in the center of the Milky Way, but there's still no way of using this technique to see other galaxies, to determine the distance to other galaxies. They're just too far away. That angle is immeasurably small. So there's a second technique, and this is called using a standard candle. So this is just the fact that if you have a thing that's bright, and you know how bright it is, by measuring how bright you perceive that thing to be, say a 100-watt light bulb, you can determine how far away it is. A 100-watt light bulb that's sitting at the other end of the room is dimmer than a 100-watt light bulb straight in your face. Right. So if there are stars, bright stars that have a known luminosity, we can use the measurement of the brightness of those stars, the apparent brightness as measured by our telescopes, to infer those distances. The thing is, we don't know how bright those things are to begin with. So we need to calibrate those stars somehow. And so these bright stars with known luminosities or with constant luminosities, usually stars are kind of all over the place. There's this category of stars called Cepheid variables that was actually discovered by Henrietta Swan-Leavitt here, who was working as a sort of computer at Harvard back in the 1910s. So she discovered this beautiful relationship between the period of these stars, they just pulse regularly, and the absolute brightness of them. But she didn't know how to calibrate those. So you need to actually, take the first one, take one of these, and measure its distance using another method to figure out, how high on this axis this entire thing is. Once it's calibrated, then you can use this relationship to measure the distance to all the other Cepheids that you see. She was prevented at the time from doing it because it was considered actual scientific investigation, and women were not allowed to do that. She was given credit for the work she did, so there you go. For more distant galaxies, stars won't do it. We need something brighter. The brightest thing that we know of in the universe are supernovae, which are exploding stars. Right. So this is what you need to do to measure the distance to stars to figure out how far away galaxies are. So first you calibrate your set of standard candles using parallax. Then you calibrate the next set. So you find a star that you can measure the distance to that is one of these standard candles, measure its distance, calibrate it, and then you find your brighter standard candle and hope that it's close enough to one of your calibrated ones to then calibrate that type of standard candle. And then you keep going up this ladder until you've calibrated the brightness of these supernovae. And then you can go out and measure the distance to anything you want in the universe. And then have massive fights about your systematic errors. So the first person to actually convincingly do this to a star outside the galaxy was Edwin Hubble. He was taking the brand new 2.5 meter telescope at Mount Wilson in California for a spin. And he discovered this little variable star here, Cepheid variable, and using Henrietta Swan-Leavitt's relationship that was had just been calibrated by the lab's leader, Harlow Shapley, measured a distance of 300 kiloparsec. A parsec is a unit of distance. It's about 3 light years. So this would be 3 times 3, about 1,000, a million light years. A million light years is way, way larger than the size of our galaxy. So this puts Andromeda far outside our galaxy. Given that it's so big in the sky, it means it's a massive thing. It is the size of the Milky Way. This was later refined to about 1,000 kiloparsecs, and modern measurements put it at about 778. So there was some error there, but factor of 2, early 20th century astronomy, pretty good. The next character in our story is Vesto Slifer here, seen about to assassinate the Archduke Franz Ferdinand. That's what you came here for, Austro-Hungarian Empire jokes. No, he's actually from Indiana. He has a cool name, though. So he measured the Doppler shift, the speed at which 25 of these nebulae, at the time they didn't know if they were in the galaxy or outside the galaxy. And he realized that they're all moving away from us really, really quickly, at velocities of about up to 2,000 kilometers per second, which is insane. We're going around the sun at 200 kilometers per second. Sorry, we're going around the sun at 30 kilometers per second. The sun is going around the galaxy at 200 kilometers per second. So this is crazy. They should all be flying. They should be gone by now. And why would everything be moving away from us? Like, do they just not like the Earth? So again, our friend Hubble, handsome as always with his smoking jacket and his pipe, made some more precise measurements now that he knew that these things were outside of our galaxy. And so he figured out, so the way you do this is you take the spectrum, you take the light from a galaxy, you decompose it, you send it through a prism, decompose it into a spectrum. These are black and white photos because at the time you had black and white photos, but this would appear blue if you're looking at it without the photographic plate. This would appear red. And you look at known atomic transitions. So if you excite, in this case, this is calcium. If you excite calcium, you heat it up, or you send light through calcium, it will absorb light at this very, very specific frequency that is blue. But just like an ambulance that's rushing away from you starts to sound lower, or a car goes from a high-pitched sound to a low-pitched sound as it goes by you, light also Doppler shifts. It becomes redder if the source is moving away from you, and it becomes bluer if it's moving towards you. And he noticed that these lines, see this pair of lines here, this is a very distinct signature, is moving to the red the further these objects are from us. Right? These galaxies, so there's the Virgo cluster, these different galaxies are further and further away from us. They seem to be moving faster and faster away from us. And this gave what we now call Hubble's law, which is this linear relationship between the distance from us, parsecs again, so remember parsec is 3 and a bit light years, and the velocity at which these galaxies are moving away from us, receding from us. So Hubble made this first measurement back in the 1920s. The telescope named after him, the Hubble Space Telescope, measured this today, and we'll get into that, to be about 72 kilometers per second per megaparsec. What that means is that every megaparsec I go in distance away from me, the galaxy that I find there will be moving away an extra 72 kilometers per second faster. Things are all moving away from us, again. So this is an empirical relationship. This isn't a theoretical law. There's actually some very nice cosmology, theoretical cosmology, that gives this in a certain approximation, but we don't need to get into that. So We seem to be at the center of an expanding sphere. Everything is moving away from us. Everyone hates us. They somehow knew about Trump. I don't know. That's going to be the last one. This isn't a violation of the cosmological principle, though. If you put yourself on, so if you put yourself on Earth, you wait a little bit, galaxies are moving away from us. The further galaxies are moving faster than the closer galaxies. If you put yourself on another galaxy, you'll notice it's also moving away from nearby galaxies. Galaxies that are further away from it also moved a larger distance. This is what uniform expansion does. The universe could be infinite. Everything is just moving away from everything else, and to every observer, it just looks like they're the center of this expanding sphere. Right? Everyone thinks they're the center of the universe. I said I would stop making depressing statements. So this gives us a clue, though. So this is telling us that space itself is expanding. The distance between galaxies is expanding. And I can take Hubble's law and I can turn it around. I can say, well, this is Hubble's law. The expansion velocity is this constant, h naught, this number, just a number, times distance. So I can ask, if I look at a galaxy that is 10 megaparsecs away, how long did it take to get there from here? Right? So distance is velocity times time. This is the only slide of math. Don't panic. I can just turn this around and say time is distance over velocity. That means that 10 megaparsecs, I just plug in the distance, divided by h naught, which is this number. Well, v is h naught times 10 megaparsecs. I have 10 megaparsecs, 10 megaparsecs. If you remember your kindergarten algebra, you can cancel these two things, and you get 1 over h naught. In fact, you get the same answer no matter what distance you put in. 1 over h naught is a time? Well, yeah, it is. So I said it's 72 kilometers per second per megaparsec. A megaparsec is just a unit of distance. So I can write that in kilometers, cancel these numbers, and I get a time, which means absolutely nothing to me. So this is 1 over, well, 10 to the minus 18 inverse seconds. That's useless. But I can say, well, 1 over h naught, that is 10 to the 17 seconds. That's more of a reasonable number. And I can turn those into years, and that is 13.6 billion years. 13.6 billion years ago, if we just follow Hubble's law, everything that we see was in the same spot. It wasn't necessarily here, right? Every other observer would put all that stuff at their position. But it tells us that the universe has a finite age. The universe is only 13 billion years old. Now, the actual physicists in the audience will say, wait a minute, you kind of cheated there. There's a 2/3. Yes, there is, and then you get the wrong answer. But if you go back and actually do it properly with integral calculus, you get this answer again. So doing two things wrong actually gives you the correct answer. It is the correct answer. But this is the resolution to Olber's paradox. Right? The night sky is actually dark because of this finite age of the universe. Light travels at the speed of light. It doesn't go faster than the speed of light. So anything, even if the universe is infinite, anything that was, whose light would take more than 13.6 billion years to reach us, we can't see yet. Its light hasn't reached us yet. The universe is expanding. It was finite. It started at this finite time. Spatially, it may be infinite. But there's this thing that we call a horizon that's preventing us from seeing beyond it just because the light from those regions hasn't reached us yet. Edgar Allan Poe actually figured this out. I'd read this quote, but it's long and I'm running out of time. So there's a little twist to this story. And this is the following, and I don't have time to go through this entire cosmological history if you want to sign up for my Astronomy 102 class. This takes about 5 courses, or 5 classes. But we're doing the CliffsNote version here. As you go back in time, the universe gets smaller and smaller. if we run the clock backwards. And if you compress stuff, it heats up. So as the universe, when the universe was younger, it was much hotter. And in fact, there was a time, which was about 300,000 years after this initial question mark here, so this entire time, where it was so hot that atoms were ionized. Electrons and protons were not bound together. And that meant that light couldn't travel very far because it was always hitting free electrons bouncing off of stuff. The universe was opaque. It was opaque, it was very hot, until it cooled enough at about 300,000 years to recombine, and light started to stream freely. And at this time, the universe had a temperature of about 3,000 Kelvin, 2,700 Celsius, and so it glowed red. The universe, at this time, emitted this red glow everywhere, in every direction. And we actually see that today, because the universe has expanded, the wavelength of that light has also expanded to the point where it's no longer red, it's actually a radio signal. It's called the cosmic microwave background. And there are these little ripples, these tiny, tiny distortions in the cosmic microwave background. This is a beautiful map made by the Planck European satellite of the entire sky. This is this snapshot of the Big Bang, 300,000 years after the Big Bang. And these little ripples are tiny fluctuations, fluctuations of about a microkelvin, very, very tiny fluctuations, that eventually collapsed to form the galaxies that we see today. But this is not what this talk is about. The only point that I want to make here is if you notice these ripples, there's this characteristic scale. It's about 1 degree in the sky. There's this, you see a lot more of these little fluctuations, these little 1 degree fluctuations, than you do, say, the larger ones or the even smaller ones. And that actually corresponds to a characteristic scale that has to do with the time it took sound waves to propagate from the very beginning of time to this epoch. And this scale, because it has to do with physical quantities, is actually means that we can use this to measure the distance to the Big Bang, to measure the distance to this surface, or rather the distance, the light, from which the light was emitted that we see now before it traveled all the way to us. And we can use this as what's called a standard ruler, sort of. I'm simplifying things a bit. But it means it gives us a different way of measuring the rate of expansion of the universe. Because the time the light takes to reach us is related to, well, how much the universe has actually expanded. And this leads us to a puzzle, because the cosmic microwave background gives us this value of the Hubble constant of 67 kilometers per second per megaparsec. And our old method is somewhere around 74. And actually, these two numbers, there are error bars, and they disagree with each other completely. And this is what the state of the art is now. So in blue, this is year of publication. This is the Hubble constant over time. It's not constant. You see these error bars are getting smaller and smaller. The value that's been inferred by looking at these distant, so these are the stars that are used to calibrate the supernova measurements. They're getting more and more precise, and they're converging on this number up here. And the cosmic microwave background is getting more and more precise. This is when Planck turned on, and it's converging on a number here. And they're in complete disagreement. And actually, just 2 weeks ago, this other group used a different way of calibrating this and came up with a number in between. And everyone went, oh, that's great. Except for the people who published these, who did a reanalysis of this and claimed that this method was all wrong. So people are discussing, it's a mess. We don't know what's going on there. It could be something fundamental that we don't understand about these supernovae, about these Cepheids, about the cosmic microwave background, and that's where the fun science happens. If you allow me an extra minute or two, I just wanted to point out that it also gets weirder. And I've been looking around, so by looking at extremely distant supernovae, you can actually show, and this was shown in the late 90s, that the universe isn't just expanding, the expansion is actually speeding up. And that really makes no sense. Gravity should cause this expansion eventually to halt and either coast or recollapse on itself. But there's something that's causing the expansion of the universe to actually get faster and faster and faster. It's impossible to find a good plot of this. This is the least bad one. This is where I make fun of astronomers. So these axes, this is earlier time. So time is running backwards here. And this is dimmer things that are up here. So this axis is also backwards, and this is the convention in astronomy for reasons that elude me to this day. It was started by Hipparchus, who's old and Greek and kind of crabby. But if you look at this, you can kind of intuitively figure it out. So the bottom line here is the brightness that you expect these supernovae to be if the universe is expanding normally, right? If it's expanding if it's just coasting, or whatever boom made it expand is just keeping going. But the supernovae that we observe are actually dimmer than they should be, implying that the light has traveled longer than it should have, implying that the rate of expansion when the universe was this old is different from the rate of expansion, smaller than the rate of expansion of the universe now. That was a lot to process in 2 minutes, but we can all sleep on it. It does make sense. But this accelerated expansion of the universe has a couple of interesting consequences, and I'm going to end soon. The main one being that eventually, because the universe is expanding faster and faster and faster, well, galaxies at some point are going to leave that horizon again. They're going to be moving away from each other so fast that the light from distant galaxies, at some point in time, about 150 billion years, I made this beautiful plot with MATLAB the other day, at some point, we will no longer see that light because the universe will be expanding so fast that the light just won't ever get to us. And that means that astronomers, in 150 billion years, a trillion years, will see this in the sky. So that means that the cosmological principle, there's no special place, special time, is a bit broken. There is a special time, and, well, it could be worse for us. So, meanwhile, there's this ongoing tension between just these methods of measuring the expansion of the universe. We know it's expanding. We don't know at what rate, and that's kind of interesting, the fact that these two different methods disagree. We really don't know why expansion is accelerating with time. I'm happy to answer questions about different ways in which this works. This is, it's a lot of fun. But in the meantime, that means that there's a lot of science to be done. So thank you.
All right, thank you, Aaron. That's a great presentation. I'd like to take a few questions from the crowd, if anyone has anything that they'd like to ask Aaron right now. Yes. Aaron, if you could repeat the question.
Oh, sure, yeah.
During the recombination period, just had a question about if you didn't have expansion occurring in the universe at that time, would it have cooled?
If you didn't have expansion occurring during recombination, would it have cooled? I would think not. If you just have the universe in a box at a given temperature, there's no way for it to cool. There's nowhere for that heat to go. So you can picture the cooling is just, if you want to think about light, which is carrying that heat information, you're stretching that light. Lower wavelength light has less energy. So you're effectively lowering the energy of all the particles. If the universe is not expanding, no, it would stay at that perfectly toasty 3,000 Kelvin. Yeah.
All right, do we have another question? Yes.
What the relationship between gravity and the expanding universe? It seems puzzling, but I thought gravity was what held resistance within it.
Yeah, so the Newtonian picture of gravity, which we all learn in preschool or wherever we do that, doesn't quite work. So to actually understand the relationship between gravity and expanding universe, you need to go to Einstein's theory of gravity, which basically says that so matter is telling the actual universe how to behave, and then the behavior of the universe is then affecting the trajectory of matter. And so your intuition, though, is correct. If I add more matter to the universe, that expansion should slow down. And if the universe had just contained matter and nothing else, then we would expand, and at some point that expansion would stop and start to recollapse again, and we would get what's known as a big crunch. Right? And that doesn't seem to be what we observe. Now, I think your question is really, why was it expanding in the first place? And I don't know. So what were the initial conditions of the universe that started that initial expansion? There are theories. There's something called inflation, in which you have some weird form of energy. It's a little bit like dark energy, like the thing that we use to pretend to explain why the universe, the expansion is accelerating today. But that kind of strange energy density would have caused an expansion of the universe, an accelerated expansion of the universe, and then when that stopped to dominate, you still have that, it's still expanding. And then the matter in the universe starts to take over. And you think you'd get a big crunch, or at the very least it would just keep coasting. But again, there seems to be this extra component, this dark energy, some people call it a cosmological constant, that's causing this acceleration this expansion to actually start to accelerate again.
All right, we got one last question from the crowd. If not?
Oh, there's one in the back there. Yep. So is this, so are you asking specifically about the concept of dark energy? Could this just be another ether? So, I mean, yeah. I'll give you a better answer than that. So the puzzle here, so we use words like dark energy to mean very specific things that we're attempting to find, and the dark matter is another one, to explain these very puzzling observations. So if it turns out not to be dark energy, if it's something a bit more subtle, if it's something we don't understand about the theory of gravity, that's entirely possible, and people are looking at that. But the puzzle remains, right? There remains the fact that we don't know what's causing this accelerated expansion. So the ether, right, so the ether analogy is that, so in the 19th century, people thought that waves need a medium to propagate in, like water waves need a medium to propagate in. Light is a wave, so therefore light needs a medium to propagate in. And the idea behind ether was, well, ether is this thing that's surrounding us that the light is propagating through. And there was a series of experiments, in particular the Michelson-Morley interferometry experiment, that went out, sought specifically to measure the presence of this ether, and the fact that they found that it's not there actually eventually led to a breakthrough in our understanding of what light was. And I think it's a good analogy to keep in mind. Physicists have certainly learned that lesson. I don't think you'll meet anyone whose eggs are all in the same basket. But yeah. As long as we don't know the answer, we'll keep looking. Yeah.
All right, let's thank Aaron again.
Thank you.
Okay, so you should all have a ticket you were given on entry, and that color code tells you where to go next. So, if your ticket is red, you will be going with me up to the observatory on the fourth floor. If your ticket is orange, you'll be going with Sean. Please wave. There you go. You'll be going with Sean up to the warm room. If your ticket is green, you'll be going with Jessica, see at the back, up onto the roof. These are all on the fourth floor, so you can follow any of us up to begin with. And if your ticket is black, you'll be going with Mark over to the visitor center. These arrows are longer because there's a bit of a lock over there. Once you get started, then you will just follow the arrow